Okay, this is the video to go with lesson 4.3. So first of all, we'll start off with the warm-up. Pause the video if you've not had a chance to try this, and then we'll look at the answers for this one. So this is really a review from Unit 3, and as we're trying to solve log equations, thankfully they're all the same base here. They're all base A, so we know we can use our rules of logs for this one. So I'm noticing things like numbers at the start, I know I can bring up as exponents, so I'd want to write this as the log of n squared. I also know things when I've got the log of something minus the log of something else. I can do a division question. So I could have n squared over 5n minus 24. And at that point, once I've got logs on both sides, I can get rid of the logs. So I could just have n squared over 5n minus 24 equals 4. And hopefully you could play around with that and come up with this. Notice this is a show that question. Even if you don't get part A, you can still answer part B. And actually 2 pretty easy points here just for factoring. And if you couldn't find out what the two numbers were, you could always use the quadratic formula as well to find those. So with regards to the homework, a few little things, particularly on question 2. People, when they substituted in x to find out what y is, the ln of 1/2, and when they looked in the back of the book, they did not see the ln of 1/2. So the important thing with this is you can split this up too. You can say this is the ln of 1 minus the ln of 2. And the ln of 1, of course, though, is 0. So 0 minus the ln of 2 just equals negative ln of 2. So that's where people were getting this negative ln of 2 from in their answers. And similar thing when you did question 2c as well. If you had the ln of 1/3 in your answer, probably that same thing. Do ln of 1 minus ln of 3. ln of 1 is 0, and then you've got just negative ln of 3. So actually, from that previous question, we have this equals this. So this is often the fourth rule of logs that people will just go ahead and just learn. And they know that when it's the 1 over something for an ln, that it's just the ln, it's the negative, ln of the bottom number. So you might see it written like this. Or you can just split it up like this each time, and that will be perfectly okay as well. Now, I did want to show question 3c. This one had slightly more work in it because you've got to find the maximums and minimums, and you've got to show if it is a maximum or a minimum. So also we've got part AICE 1 here and part AICE 2 question here. So differentiate x squared. When we're doing the differential of this one, differential of x squared is 2x, and then put it over the original, which is x squared, and with the negative sign here. Personally, I would have brought the 2 to the front and put negative 2 ln of x, and I know the differential of ln of x is 1 over x, and 2 times 1 over x is 2 over x. So you could simplify this process a little bit, but I think most people would just go ahead and do this. Also, we're setting this equal to 0 because that's how we find our maximums and minimums, and then we go ahead and simplify. Then trying to solve this equal to 0, if we multiply throughout by x to get rid of this fraction, then we have this, which nicely factors, and you'll end up with two values, 1 and negative 1. Now to find out if they are a maximum or a minimum, you have to differentiate for a second time. So from this point here, this is probably the easiest place to differentiate this one because it's actually simplified. Differential of 2x is going to be 2. You have to rewrite this as negative 2x to the negative 1 and then differentiate. But you should be able to come up with this expression here. Plug in each value as you go along, and they both turn out to be greater than 0, and when they're greater than 0, we know that is a minimum, which I didn't actually write here. Now, I noticed for the homework, quite sensibly, some of you actually checked using technology. You actually graphed just to see what the original function looks like. And you can indeed see that there's a minimum at negative 1, and there's a minimum at positive 1. Both are valid, but the textbook does not include x equals negative 1. Now, we do have to check to make sure we don't get the ln of anything negative here. But if you do the negative 1 squared, you'd end up with positive 1. So that shouldn't be a problem for this question, as you can see from the graph here. Question 6, just in case you wanted to see this one, differential of 2x minus 3 is 2, and then put it over the original. To find the slope, substitute in the x value, and as this question says normal, don't forget to do the negative reciprocal. They gave us the x value but not the y value, so to do that, plug in here. 2 times 2 minus 3 is 1, and the ln of 1 is 0. And then you can go ahead and use the point slope formula. They had the answer in a very strange form, but you should still be able to show that your answer equals this. I think most people put y equals negative 1/2 x plus 1, and I would have done as well. If they would want this form, they would have to say show that you can write the answer in that form. And if you want to see question 7, we'll wait until we did it at the end of the lesson, but I'll do it at the end of the video if you want to see that question. So let's move on to the lesson proper today. So lesson 4.3 is integrating to get the ln function. So notice the wording is kind of very careful here. I'm not integrating the ln function. We're going to integrate to get the ln function. So last lesson we differentiated. So we're going to start with this one here. So if I differentiate this one, the differential of 3x plus 5 is 3. And then I would put it over the original. Now the reason I'm putting that here then is, if I was to ask you what is the integral of 3 over 3x plus 5, then it must be this, because we just work backwards. Of course, plus c as well here. And also when we integrate this type of function to get the ln function, we also put absolute values here, just to guarantee that we don't get something that's negative as well. So the basic rule we're going to be using for this lesson is we're going to be checking. If we have a fraction that we're integrating, one of our first checks is going to be, is the top the differential of the bottom? If it is, then the integral is going to be the ln of the absolute value of the denominator plus c. If it's not, it might just be a regular integral where you just bring the exponent up to the top, give it a negative exponent, and then integrate like you did in AICE 1. But this is an extra method you need to check now when you have fractions, just to see is the top the differential of the bottom. Now we've got a few questions to look at here. So for this one here, you can actually see the differential of the bottom is 4, which is exactly what it says here. So this would be the easiest question. Whoops, I realized they were all grouped together there. So it would just be the ln of what you see on the bottom, or the denominator, plus c. Now this question here is obviously very similar to this question, but notice now the top is not the differential of the bottom. So what we have to do is we kind of have to fix this a little bit. It's kind of a bit like completing the square. So I know that I want it to say this, so the top is the differential of the bottom, but I also know I need to make 12 here as well. So I got to think, what do I have to do to this to make 12? Well, of course, if I times it by 3, that would give me 12. And then now I can write down the answer straight away, because it's 3 times, and then this is the ln part that I was really looking for. And if I did the same here, I would have to fix this question a little bit. I want it to say 4, so it's the differential of the bottom. But then I've got to make sure I actually end up with 2. So 4 times by 1/2 would give me 2. And then therefore I can say it's 1/2 times by the ln of that value. So a lot of this is just simple manipulation of numbers just to make sure it works. If we get a slightly more complicated question here, the differential of x squared is 2x, and the differential of 2 is 0. So actually the differential at the bottom is 2x. That works perfect for this question, so I can just say it's the ln of x squared plus 2. Now if I try it for this question though, I know the differential at the bottom is 2x, but that's not quite what I've got here. But what do I multiply 2x by to get negative 14x? Well, that would be negative 7. And if I can do that, then I can write down what the integral is as well. Same for this one, then we know the differential at the bottom is 2x. That's not quite what we have here, but I know that if I multiply by 1/2 times 2x, then I will get exactly what I want. So I can say that the answer is 1/2 ln of x squared plus 2. So just a little bit of fixing. If the top isn't exactly the differential of the bottom, but it's a multiple, then just make sure that you bring that number to the front and then leave what you actually need here to be the differential, and then you can write both parts out separately. Now, a lot of these questions, though, really we want to look at previous exam questions so we can see exactly what they look like. So here's one from 2007. We also have limits here, which shouldn't be a big problem for us, but we've got to show it's equal to something specific. And this actually goes back to the lesson from the previous unit, actually. But let's do the first part for this. So the differential of 2x plus 1 is 2, which is not what I have on the top, but I can easily make that as a multiple of that. So I wanted 2, and if I times it by 1/2, I get my 1 that I'm looking for. Once I've done that, I can now say it is the ln of the denominator between those two limits, and then I can plug in those limits as well. So if I plug in 4 into here, I get 9, and if I plug 1 into here, I get 3. So we've got 1/2. Now I've actually put the 1/2 to the front, and because I'm going to multiply both of these things. So I really should have put parentheses here just to make that clear that it's not just 1/2 times all of this. Use my rule of logs here. So when I've got, actually I did put the parentheses in here, I'm sorry. I put it in one line later. And then using my rules of logs, I can say it's this divided by this, and 9 divided by 3 is 3. And that's actually what it asks us to do in the question, as you can see. This is from 2011, same sort of idea. We can see that we've got an integral here. The differential of the bottom is 4. So that's not quite what we got here. But once again, we can take a multiple out at the front. So if we take 1/2 out at the start, then now the top is the differential of the bottom. And therefore we can say it's the ln of the denominator. And I realize that's kind of a complicated thing here. And I've got so used to doing this, I haven't really elaborated on this. Although we're doing an integration question, the first thing I actually checked is what is the differential of the bottom. So I know that's sometimes something that students struggle with initially as well. Once we've done our integration, go ahead, plug in those limits. So 6 and 2. 4 times 6 plus 1 is 25, and 4 times 2 plus 1 is 9. I was good enough to put the brackets around the half this time, so I can use that same rule of logs again here, and then I can just factor out the 1/2. 25 over 9 doesn't really simplify particularly nicely, but notice I can bring up this 1/2 here as an exponent, and then actually I can do this. So the square root of 25 over 9, square root of 29, from 25, sorry, is 5, and the square root of 9 is 3, and then we get exactly what we're looking for here. So a half is kind of a common one to use because they want to check, do you understand what we're doing with radicals? Questions can get dramatically more difficult. So one of the higher level questions would certainly be a volume of revolution question. So the region under the curve with equation this is rotated through 4 right angles or 360 degrees. Find a volume between 3 and 8. So this might not look like the type of question at all, particularly with the square root here, which we didn't have. But let's start off with the question that we actually know. So volume of revolution around the x-axis, we're going to use pi y squared dx. And then when we square both of these, 1 squared is 1. Of course, the square root of something squared just actually gives you the fraction itself. And then now this does look more like the question we were actually looking at. So the differential on the bottom is 2, which is not what we have here. So we've got to fix this question a little bit. So if we bring a half to the front, a half times 2 is 1. And also we have the pi here this time as well. Once we have that, we can say it's the ln of what's on the bottom with absolute values. And then we can just plug in those numbers and I'll reveal the rest of this then. So when you plug 8 into here, you get the ln of 15. When you plug 3 into here, you get the ln of 5. And using that rule of logs again, 15 divided by 5 is 3. So perhaps possibly not even as difficult as it might first look, and possibly even easier than some of the questions that you saw in AICE 1 as well. If you want to review the revolution around the y-axis, there is a question 9 from 4C that I would recommend that you take a look at as well. And since I last did this video, I've also got a very recent question. Not that this exam actually happened, but June 2020, if we had have had that exam, then we would have had this question here. Now this one is quite a bit more difficult, which is why I included this one. Instead of giving you actual values here, they've actually just given us a limit and called it a, but they've told us what the integral is. So I thought this was a good one to take a look at. Notice for this one, the fraction, if you differentiate 2x plus 1, you get 2, so it's not quite the same as the top, but we should be able to easily fix it by bringing a 2 to the front, and therefore we'd have 2 ln of 2x plus 1. Also, just to make sure we're paying attention, they have thrown an AICE 1 integral in here as well. So the integral for 8x would be 8x squared over 2, which would simplify to 4x squared. We know we have these limits, and then we should really say equals 10 here. I'm not quite sure where that happened. I put it on the next line. And then let's plug in the limits. So wherever it says x, we're going to plug in a, which doesn't do much for the first set of parentheses. When we plug in 0 here, we get 2 times 0 plus 1, which is obviously 1. 4 times 0 squared, which is 0. The ln of 1, of course, is 0, so actually this whole second part is 0, so I can now just write this first set of parentheses equal to 10. Now, I'm going to start looking at my answer here, because this is a show that question, so I've got to try and get to this. So one thing I noticed straight away is actually I've got a's on both sides, which we don't normally do. I also know there's a square root here, so I'm noticing there's a squared here, so that must have something to do with this. And I'm also noticing it says a, but this says 4a. So I've probably got to divide by 4. And I'm also noticing this connection here as well straight away. The fact that it says 10 and this says 2.5, which is 10 divided by 4. So I'm going to divide throughout by 4 2 divided by 4 is 1/2. And then I can start bringing terms to the other side. I'll try and leave that top line in if I can so we can still see it. So bring this to the other side and subtract, and now we can see it's looking exactly the same. I put 1/2, they use the decimal, and then you can do the square root, and it's exactly as it is supposed to be. There are questions for this, and if you go and look on the relevant place, then you'll be able to do those exercises. That does it for this video, though.